This video is about electric current and voltage. We will cover the energy and potential difference in circuits. Current is the rate of flow of charge, following the relationship. Charge equals current multiplied by time. Electric current in solid metallic conductors is the flow of negatively charged electrons. Voltage is the energy transferred per unit charge passed, where 1 volt is a joule per coulomb. An electrical conductor, like all metals, allows electric current to flow easily. Electrical insulators, on the other hand, have a very high resistance to current flow. Electric charge can be either positive or negative. Electrons carry a negative charge equal in size to the positive charge of a proton. Neutrons have no charge. An atom is uncharged when it has the same number of electrons as protons. Electric current is the rate of flow of electric charge. 1 ampere flows when 1 coulomb of charge passes a point in 1 second. In metallic conductors, electrons carry negative charge from the negative side of a power supply around the circuit and back into the positive side. The charge-current equation is electric charge equals current multiplied by time, or Q equals IXT. This relationship can also be rearranged to find current, I equals Q divided by T, or time, T equals Q divided by I. Let's work through an example problem. Calculate the charge passing through a device when a current of 500 milliamperes flows for 3 minutes. Using the formula Q equals I times T, 500 milliamperes multiplied by 3 minutes is converted to standard units as 0.5 A multiplied by 180 seconds. The resulting charge is 90 coulombs. Here is question 2. Calculate the current flowing when a charge of 240 coulombs flows through a device in 80 seconds. Using the rearranged formula, I equals Q divided by T, 240 coulombs divided by 80 seconds results in a current of 3 amperes. Now complete the table using the charge-current equation. Here are the answers for the table. The missing values are 30 seconds, 65 coulombs, 3 amperes, and 60 seconds. Voltage is the energy transferred per unit charge passed. Voltage is equal to energy divided by charge. 1 volt is equivalent to 1 joule per coulomb. Here is a question on voltage. Calculate the voltage of a battery if it supplies 300 joules of energy to 50 coulombs of charge. Using the formula, voltage equals energy divided by charge. 300 joules divided by 50 coulombs gives a battery voltage of 6 volts. Now let's complete this table using the relationship between voltage, energy, and charge. Here are the answers. The completed values are 40 coulombs, 20 volts, 120 joules, and 300 coulombs. Choose the appropriate words from the selection below to fill in the gaps in these sentences. Electric current is the rate of flow of electric charge, which is measured in coulombs. A battery provides electrical energy. The amount of energy provided per coulomb of charge is equal to the voltage of the battery. The main supply gives 230 joules to every coulomb of charge. Electric current will only flow if there is a complete, unbroken electric circuit with a power supply. Circuit diagrams use standard symbols to show how electrical components are connected. Circuit symbols include the cell and battery, which push electrons around the circuit. Wires connect components, and a wire junction indicates connectivity. A switch turns the current on or off. Other symbols include the indicator, often a light bulb, to show if the circuit is on. The ammeter measures current in amperes, and the voltmeter measures voltage in volts. A fixed resistor limits current, while a variable resistor allows resistance adjustment. A thermistor's resistance decreases with temperature, and a light-dependent resistor's resistance decreases with brightness. A diode allows current flow in only one direction. An LED is a diode that emits light. A fuse melts to break the circuit if the current is too high. A heater converts electrical energy to heat. Electric current flows from the positive terminal of a power supply, around the circuit, to the negative terminal. The longer, thinner line of the cell symbol is the positive terminal. Match the correct circuit symbol to the name of the component. The correct matches are ammeter, diode, indicator, heater, thermistor, cell, LDR, and resistor. Here is a question to test your knowledge. Draw a circuit diagram for the torch shown in the image. Circuit components connected in series mean the same electric current passes through each component in turn. This diagram shows a series circuit where the cell and 2 lamps share the same 3A current. In a series circuit, one switch can control all components. The components share the power supply's voltage, so adding more bulbs in series makes each one dimmer. In parallel circuits, the voltage across each component is the same. Therefore, the voltmeter reading across component X, V1, is the same as the reading across component Y, V2. Parallel circuits allow individual control of components with separate switches. If one light bulb breaks, the others continue to function. This is in contrast to series circuits. In parallel circuits, the total current is the sum of the currents through the separate components. For example, 5A splits into 3A and 2A, and then recombines to 5A. What are the advantages of connecting two lamps in parallel rather than in series to a power supply? In parallel, the lamps are brighter, they can be controlled individually, and one lamp will continue working even if the other does not. Let's calculate the currents measured by ammeters A1, A2, and A3 in this parallel circuit. We are given the total current, 6A, and the current through one branch, 2A. The total current measured by A3 is 6A. Current A1 is 2A as the current splits. Current A2 is the remaining current, 4A, since 6A minus 2A equals 4A. Now, choose the appropriate words from the selection to fill in the gaps for these statements about series and parallel circuits. When components are connected together in series, they all have the same current flowing through them. In parallel, they each have the same voltage. Lamps are usually connected in parallel, allowing individual control by switches, and if one lamp blows, the others still operate.